Hi, I hope internet works. I can see it's working now, but then it stops. Suddenly it stops. Maybe. So, guys, hi Vedant Pandey. I hope it works. I hope it's working. Can you guys confirm, like, if you can hear me or if you can? We are going to solve code forces problems, right? So let me do that. It's working fine, right? So far, it's working fine, and you guys can hear me. So let me create a new folder, and then we will solve CF problems better than Coach F problems, right? I'm sorry, Coach F. I don't know. I need 10 viewers, guys. Like the video, and we need 10 viewers to start with. Then only then I will share the screen and solve code forces problems. Explain them in the best possible way. So you guys can't get such good explanations elsewhere. Should I give virtual? Should I give virtual? Then you guys will know that I cannot solve problems, right? Okay, I'll give virtual for this stream. We have more than 10 viewers. Let's go virtual. We are giving it virtual. How to give virtual? I should not see standings for that. Right? I should not see dashboard too. Because if I see dashboard, I will get some understanding, right? So I think we have to wait for that. We have to wait some time. Right. I think it's system tests are running. So I think system tests are running. So should I try for virtual? Mike is being more innovative than any other company, I guess. Right. So say guys, haven't I registered for this yet? So I think I cannot give virtual. Let me close this solve spot, and then I look if I can give virtual. I have closed with hand, so I cannot see. I cannot see. Problems look nice. Increasing sort makes make good. Inversion name sounds good. 82%. We have to wait 10 minutes. Okay. By then 10. Coach F. Let me see Coach F problems by then. Okay. Let me see Coach F problems by then. If you guys, and then I will go and try to give it virtual, right? I can solve. You guys will get to know that. When did it happen? Where are they? This one, September 17, rated till 5 stars. Let me go to this one. We have 40 solves, 6 solves. Let's read this problem once, and this two. Maybe this two. Okay, we are here. Let's read this. Okay, let's read this without getting scared. Chef constructed a tree with n vertices. Tree is not something complex, guys. Tree is a simple and one of the simpler data structures. I would say tree is more simpler than tree or graph is a more simpler data structure than set, probably, right? You don't know what the hell how the hell set works. It's binary indexing tree or something. But then graph is simple. You have elements, you have pairs of elements, edges or pairs of elements. Graphs are simple. We have this tree of n vertices, generate a random array of size n minus 1 where pi less than or equals to I, 1 less than or equals to pi. So we have n minus 1 vertices size. All possible array satisfying constraints are equally likely. So each of that array is equally likely, it seems. Each of that array is equally likely, which also means all of them are equally likely, probably, right? Create a tree with only one vertex labeled 1. For each 2, 3 up to so on in, add a vertex labeled I to the tree connected with an edge. Okay, we are just forming the tree. So P1 will give wherever 2 goes. P3 will go wherever P2 goes. Whatever is P2, we attach that to that. Okay, this is a very famous representation, right? But then we are generating this tree randomly. So we are generating some random tree. That's the question so far. Okay. Find the probability that the tree has a perfect matching. Output the probability modulo this. Find it can be. So this is a direct question. This is a direct question. If you guys haven't read this problem, because why is it direct? First you have to work on when can you have a perfect matching, and once you know when can you have a perfect matching, you have to think and count that when these many arrays are there. Equally probability nothing. Probability just means all possible arrays, right? Probability means just go over all possible arrays, and then you have to count number of things has a perfect matching. So you just want to count number of things that has a perfect matching. That's the problem. Is this clear till here? It doesn't mean anything about probability. Okay, till then play smash cards, guys. 38 viewers. I think these people are random people, right? Like that go over reels, and then maybe I pop up somewhere and then they click on that, right? So it's clear, right? So far problem is clear. We have to first understand when there is a perfect matching. There are some in graphs, there are some things that says when there is a perfect matching. I know the theory, but let's think without that theory. Okay, I know the theory. Like I know that's what is the algorithm. It's Tun's theorem. It's Tun's theorem. Is it Tun's theorem? No, it's not Tun's theorem. It's I'm not getting the name. It's Tunkun's theorem. Is it Tunkun's theorem? Tunkun's theorem. Tunkin's theorem? No, I forgot my graph theory or what. Now, what is the theorem that says if you remove one vertex, a number of odd components is greater than one? Sorry, after you remove this, if number of odd components, after you remove one vertex, and then the number of odd components formed is greater than one, means it's impossible. Kuntun's theorem, I'm not getting it. So, for the existence of a perfect matching, I'll tell you guys some graph theory, little bit of graph theory, okay? So, one necessary condition is, let's say there is a perfect matching, means everything has been matched perfectly, right? Everything has been matched perfectly is a perfect matching. You guys know matching, right? In childhood. So, perfect matching means given there are so many things, you can match few things like that. Given there is a graph, weird graph. But then, one obvious necessary condition is take an vertex. Okay, it has some edges, right? Remove that vertex. Now you have components, right? Now you have connected components. If odd components are greater than 1, means if you, even if that means you cannot pair, right? If odd components are exactly 1, then you can pair these two. But if odd components are greater than 1, all these should be paired among themselves. But then one will be left out. That this can help that maybe all odd components are, because odd components means there is no edge between these two. So it's obvious that odd components are less than or equals to 1, and it fails if odd components after removing one vertex is greater than 1. Okay, let's say this is not one vertex, maybe some subset of vertices. Let's say this is some subset of vertices. You remove this subset, then if number of odd components greater than this subset size, then it's impossible. This is a necessary condition, but then in graph theory, as I've always told you, we have these tone costs. The obvious necessary conditions are sufficient somehow many times, and then that's sufficient. It can be proven that that's sufficient to form a graph, a perfect matching. If this satisfied for all subsets, even if it fails for one subset, it's simple. Is it gone? Is my internet gone? So guys, do you get that? Okay, it's a bit complex, but light. It's a bit complex. Probably that's not needed for this tree problem, because this is for graphs. For graphs, it is take any subset, you remove this thing, number of odd components greater than this, impossible. Else, there is a perfect matching. There is an algorithm too. Okay, maybe you can find maximum matching itself. Maximum matching would be perfect matching. But now, here, here, I think here I think this is true. Maybe here we can just think of leaves. For a tree, when does a perfect matching exist for a tree? What happened to my VS Code? So when does a perfect matching exist for a tree? We can think of the leaf maybe. Leaf must be attached to its parent, right? Leaf must be attached to its parent. So what are some necessary conditions? So leaf must be attached. Only one leaf must be there. This we can easily see. I mean, you can try applying this theorem, and there is a simplification of this theorem for graphs, for trees, which would be if you remove any one vertex, probably you should not get more than one odd component. That is for trees. For graphs, it is subset. I think for trees, just one vertex is enough. If you remove one vertex, you should have no odd components. Sorry, it max one odd component or exactly one odd component. Why? Everything else is paired and this partner would be left, right? So let's try to prove this one. Okay, let's say this is true for all small subtrees and then you have this one vertex. Okay, so let's say that this statement is true for all smaller subtrees. If it is true for all smaller subtrees, can we prove something like once you remove this, I'm thinking, because this size is now odd. This size, once you remove this, if this size is odd, this edge would be in the matching. Wait, I'm not able to think much, but how can we prove this well? But then let's keep the proof aside. Let's just look at the graph. Probably if you remove one vertex, if you get more than two odd components, it's impossible. That is for the structure. So we have to make it a bit more clear. What's the structure for a tree to be able to form a perfect matching? See guys, most CF questions doesn't need you to know these algorithms, right? Really, that's Kunz algorithm or theory perfect matching theorem. It is Hall's algorithm, Tutt's theorem. For bipartite graphs, it's Hall's algorithm, Tutt's theorem, not Kun or something. It's Tutt's theorem. Okay. We don't need to know all these things for most Codeforces questions. Even for this question, we need not know. I am just telling for no reason. I'm just telling because I can. We need not know them. We need not know them. Probably it will be more simpler. Because if you look at one leaf, it should be paired with paired with its parent. Right? And then you remove those two. And then again it should happen. It should keep happening. And then again it should keep happening. So what are the necessary and sufficient conditions now? Like we have to think a bit more clearly. Okay. One thing is I know. Remove any vertex. If it forms even number of components, then you are good. Then you are good. I know that. But other than that, we have to think, right? See, we have to simplify the structure somehow. What does implies and implies? That hey, why are this? So we can solve this, guys. Let's try for some time. Let's try for some time, okay? Let's hope for some time and then I'll give virtual. Let's try. Let's try a bit more. It should be paid with its parents and then we can remove that. But is there a way? to represent this whole thing. Okay, we can see we can see the theorem. We can see the theorem maybe based on this leaf. Let's say you take any tree. If you look at one leaf, they both must be paid, right? And then now we have a smaller tree. So maybe in this tree, anything you remove probably should form implies and implies, because this is connected to this sum tree, right? And this will not affect the parity of that component. So probably anything you remove implies and implies number of odd components will be one, because you're able to remove a leaf. I think in that way it works. Inductively it works out. Like the condition to be, if you remove one vertex, only one odd component should be formed. Everything else should be even. You can prove it by induction, maybe. Let's say, look at these two things, keep them aside. You have lesser number of things, and remove anything. If this is having a perfect matching, this must be there, right? So if this is having a perfect matching implies and implies, remove anything, all the components will have even things. But these two are anyway even, and they must be together. So I think it works out. That proof will work out that for graphs, it should be for all subsets. For trees, one thing is enough. So we very well know if this satisfies, it works out. But then we have to be a bit more, we have to be like, is this complex thing necessary, or is there a simpler thing we have to look at? Because if you remove something and then even number of things, number of odd components is exactly one, then you are good. Okay, for number of components to be exactly one other than this, then you are good. That's one implies and implies thing we know. That's one necessary and sufficient conditions. But can it be simplified, or can we count that itself? Is the question now to us. Can we count that itself? Number of ways you can get that. So we have to think some more time. Let's think some more time. All of them should be even sized components. Most of them. If you remove one vertex, it should leave most of them as even length subsets. Okay. Oh, it should leave them as even length subsets. Only one odd length. We are not going anywhere, but let's think. We have to count this itself, because there is a simple way to do this. What is n? Let me check 1 second. Maybe we will do this because it's counting problem. N can be 1 to 10 power 4. So is n square possible? Maybe n square is possible, right? Maybe n square is possible. So we have to think, if n square is possible, how can we solve it? How can we solve it if n square is possible? We have to count such a way all the configurations where if you remove one, even number of sizes are formed. Maybe can we fix, maybe can we, because we need not use this theorem too, because using this theorem it will be much more difficult, because no one knows this much theory, right? No one knows this algorithm, right? Maybe we can just use this thing. Maybe can we just use that leaf must be attached to its parent, and nothing else should have, nothing else should have this parent. Let's think of this thing. Okay, so now if we fix, let's look at n, because n square, because we can do n square things. I'm trying to look at n. Let's look at n. Its parent would be some v, right? If we brute force these two things, can we brute force the structure? Let's think of this problem. Let's say we are brute forcing these two things. Okay, we are brute forcing these two things. Now what is happening if you brute force those two things? Let's say we have n, the particular vertex n, and then we are fixing its vertex, its parent v. N must be a leaf. Why? Edges are from 1 to 3 up to so on forward, right? Edges are like to be before them, right? So one n is definitely a leaf. So if I fix that n attaching to v, we have we cannot have anything. Why? Okay, we can have things, but then it should only have even components, right? It should only have even sized components. Also, it should also have, so there are few conditions. It should also have, once you remove 1 comma v, if these two are removed, what should form is even sized components that can form a perfect matching, right? Okay, it's not that simple. Okay, this proof is wrong because I thought that should be attached directly, but the proof is this. So let's think some more time. Whatever, if you fix n and if you fix this vertex v, you have some smaller sized components that can form a perfect matching, right? You have some smaller sized components that can that can form a perfect matching. Okay. Can we find this thing itself? Can we find this thing itself? Is what I'm trying to see. Okay. How can this be viewed? All of them are, all of this can be formed perfect matching. All of this can be formed perfect matching. So should I quit? Should I go for virtual? Let me come back here later. Okay. Let me come back here, guys. We'll do virtual contest. I'll come back here later. Let me do virtual contest. Okay. I hope it's done. But how to start a virtual directly? My last virtual was 2024 April 26. Now we are going to give this virtual. Oops. It takes 2 minutes. Let me change this to 03. We have to wait, guys. We have to wait. Let me think of the problem, the previous problem a little bit. Can I fix one vertex v? Can I fix root and think? Can I fix root? Can I fix root? Now what should happen? From root, maybe only one odd component should form, right? And we can brute force this probably. So if the size is odd, how to form a perfect matching such that root is left out? Else, how to form a perfect matching? If you have these two things for all n, I think we can extend. We can remove root. One is odd. All of them are even perfect matchings. Maybe we can extend. So it's done. This is done. Brute force root. Root is one already fixed. And then you have to, one is odd component. Other things are even sized components. And then number of ways you can, it's about selecting one odd component and many even components. It's done. It's done, guys. I will go back to that after this virtual contest. Okay, it's almost done, probably. Given a subset of vertices, number of things, if the size is even, number of things you can form perfect matching. If it is odd, leave root ahead, root alone. Number of things you can form perfect matching. Okay. Why? Because when this is odd, when size is even, root must get attached to one of its children, right? Then what happens? All other things will form perfect matching, and all other things must form perfect matching. Okay, that's how we can solve the problem, the previous one. Just brute forcing root is being enough. If you have it for all sizes, maybe we can do it. I will do it later. Okay. So now I will get 600 rank or 700 rank. Then I cannot. You guys will stop watching my videos or something like that. Okay. If that happens. You're subtracting n into n minus 1 by 2. So if it's not possible that you can subtract, you can use all of this, it's impossible, right? You're subtracting n into n plus 1 by 2. You're subtracting every fucking thing. Means 1, n and n minus 1 should be beside so that you can make n and n minus 1 equal. And then n minus 1, n minus 3 should be aside. 4 should be aside, 4, 3, 2 should be aside up to so on. So here it's no, here it's no. How the fuck can I code this well? How can I code this well? 4 3 should be common, 3 2 should be common, up to so on, right? If I come from above indices, if I come from back indices, if I come from big indices, then all of them should be forming a line segment, right? Oops, what the fuck have I done? So let me maintain p inverse to know their indices. Now int, okay, C out s ln. Let me have bounds for the range that I'm trying to count. The range, if it's not equals to n minus I plus 1, number of things currently we have, it's no. Why? We have to subtract everything. We have to utilize each subtraction, right? If we cannot do that, we're probably doing something wrong. We're subtracting n into n plus 1 by 2. If we cannot subtract every fucking thing, then we cannot probably do that. Right? And to subtract every fucking thing, you have to use 1 on that, 2 on n comma n minus 1 up to so on. I hope it's true, it's correct. Yeah, it worked out. You want to buy n products with prices 1 up so on, you can either buy product individually paying AI coins, or you use a discounted voucher to buy it as part of a group purchase. We have some group purchase, we have some individual purchase, you have K discount vouchers with values B1, B2 up so on BK. A voucher of value X allows you to select exactly X products and pay only the X minus 1 most expensive ones. Most expensive ones. Okay. If you select a group, one thing will be left out. Okay. So we have these vouchers. You can, as such, you can also consider the cheapest product in the group is free. Yeah, that's what it means. Each time, each product can be included in at most one discount group, even if it is not the free one. Otherwise, yeah, got it. Otherwise, we will keep one bigger thing in everything, right? And then we can get more discounts. So we have to split them disjointly and then we can ignore one thing. Okay, what's the minimum total cost required to purchase n products? Minimum cost. Maybe we have an upper bound, right? Maybe we have an upper bound. And then we have B1, B2, up so on BK. We have K vouchers. So if you have many ones, ones are good. Ones make them free. Ones make them entirely free, right? And then we have twos, and then we have threes, up to so on. Maybe we have to use all the ones possible in the beginning. Okay. And then using two is better. Is using smaller thing is always better than bigger thing? Maybe it is. Right. And then can I just brute force from smaller values of b to using smaller value of b is better, and then using removing bigger values of a is better? Can I just brute force that thing? Maybe that works, but maybe if it doesn't, how can I prove that that greedy is the best thing we can do? It seems it is, because let's remove all the ones. Okay, whatever ones are, using them to remove the biggest thing seems the best thing, right? And then you have twos. With twos, with existing only twos, if everything is greater than or equals to 2, you can definitely not remove the max element. Whatever it is, you cannot remove it, right? So now you remove use 2 to remove max minus 1. So using 2 is seems to be the best, right? So I will just brute force that greedy way. Okay, we have AI sorted. As long as ones are there, remove. As long as twos are there, you remove two things. As long as twos are there, because that's the best you can do, right? Wait a minute. Yeah, that's the best you can do. As long as threes are there, you cannot remove this one now. But then you can remove all of these smaller things. And then when a three comes, you must keep that. And then you can remove all of that. I think this works. Every time we remove one element, I think this works. Maybe keeping them as a vector and then removing back seems to be working, right? So let's do that again. Maybe this works. I need not try to prove it very well because it's virtual contest. I have to go a bit faster too. I think it seems good enough proof. Right, for B. Good enough greedy. I won't go too much into this, okay? Are they sorted? Why the fuck not? So we are having whatever cannot be saved, right? We are having whatever cannot be saved. Lost thing cannot be saved at sometimes. And then everything else can be discounted. We have to remove those two things whenever there is a two, because you cannot include this in other things, right? And then you have to remove the next two things. Okay. While I greater than 0 and j less than k. While I greater than or equals to 0, you have to add them to the cost. Answer plus equals to a of I minus minus, let's say, because these things have not been removed without any discount coupons. These things we can use discount coupons, and then if you can use b of j discount coupons, okay, b of j discount coupons means you must take top of that many, right? Mm, in f equals to 0, f less than k, b of j f plus plus, okay. For these many things, you must take v equals to 1, everything will get discounted. You have to pay for most expensive I things, right? And then I'm just doing bj minus 1 things, okay, j plus plus. I think we are good. I have to also do I minus minus once again, because also that has been done. Hope this works. It's just brute force. It's just some greedy, right? It's just some greedy. So I think this is right so far. What if the group size is small? Exactly X. Wait, because of this is our whole thing wrong. Because of this is our whole thing wrong. Now we have to pay for all of these things, right? Now we have to pay for all of these things. Could we have done better? Could we have done better by choosing something else? Probably not. And b of j greater than or equals to I plus 1. Because we have I plus 1 things, if b of j is less than or equals to I of j, until only until then I'll continue, right? Maybe it works. Maybe this greedy works. I haven't proved well. I agree that I haven't proved well, but it's contest. Let me go to C, let me go to D1, let me go to D2. Okay, that's accepted. You're given a tree consisting of n vertices, numbered from 1 to n. Each of the n minus 1 is associated with two non-negative integers x, and by consider permutation p of integers 1 to n, we have permutation, we have a tree. Each of the n minus 1 integers is associated with two non-negative integers. So each of the n minus 1 integers is associated with two non-negative integers. Seems good so far, because each edge has two integers, it seems associated with it. Are these the edges? Consider permutation p of integers 1 through n, where pi represents the value index assigned to vertex I. We have permutation 2. This, you guys may get scared of this, but then it's an easy problem probably, because it's C, right? So it's like they try to scare you. But you should not get scared. For an edge u comma v such that u less than v, the associated values x comma y, if okay, so x and y are not u comma v, I'm happy with that. Its contribution is defined as follows: if pu is greater than v, we have to take x. If pv is great, okay, whenever the smaller value has a higher value, it's like an inversion, then you have to take x. Whenever the bigger value is having higher value, then you have to take y. Okay, we got that. The value of the permutation is sum of contribution of all edges. Your task is to find any permutation p that maximizes this total value. So maximizes means if the problem is actually finding a maximum, it may be more difficult, right? Maybe it's always possible to take whatever is maximum among these two, right? Maybe it's always possible. You have to guess like that. That's an upper bound, right? Summation of maximum of x comma y is an upper bound, right? Maybe if that upper bound is possible, maybe that's the answer, right? If you think about proofs, that's a simpler proof, right? Okay, maximum of x comma y is always possible. So you have to think, is there a way that that's possible in the first step? Is there a way where I can always keep maximum of x comma y to be the bigger one? So we have many edges. We have a tree. Let's take one vertex v. Okay. Let's take one edge v. Okay. Let's take one edge v. If, if, okay, I get it. To make, that's possible. That's possible. Always that's possible. If I keep an directed edge from higher value to lower value of x comma y, if I keep a directed edge, all we need is a permutation where this thing has a higher value, right? Where this thing has a higher value. So now what do we have? Now, as long as there is no cycle, because it's a tree, you have a directed graph. As long as there is no cycle, you can keep n there, so that you can always get summation of max of x comma y by just doing this. But now how do I do that? Now how do I do it? We, whatever has zero incoming edges, I'll keep n there, and then I will remove the incoming edges, and then I will choose the next one, and then I'll choose the next one. For speed, I'm not looking for O of n. I will just go with n log n thing, the idea that I had. Okay, I will not go over n of O of n or anything like that. Okay, all we need is just in degree. Now I am trying to get in degree, right? Is x less than y without loss of generality? No, but u less than v without loss of generality. A bit without loss of generality, right? So whatever, if x is higher, means I have to make an edge from u to v, right? If x is higher, u to v there is an edge, means in degree of v plus plus. Else in degree of u plus plus. Okay, I'll maintain a set. I also need adjoint vertices, right? So I will change in degree of use. And then once I have v, p of v equals to val minus minus. This works. So how was I able to solve this very quick? Because I guessed what can there be a simple proof for this? I guessed that. How it works. So should I verify for this very quickly? How quick I can verify for this? Because there can be multiple answers, right? It's not like a restricted one. So is there a diagram for this? Can I just verify that quick? I don't care. I'll just submit it, I guess, because I cannot be wrong, I guess, right, with this solution. Unless I made some very stupid mistake. The fuck has happened? Guys, is my internet there? Yeah, it's there. So now we have to solve the problem. Inversion graph coloring. The fuck? I want to know if it is passing or not. Accepted. We are so good so far. 11 minutes, 8 minutes. I took lesser time in this than B. See that? See that proves how can Beck is so good. A sequence B1 B dot on BK is called good if there exists, and counting I'm definitely good at counting. A sequence B1 B dot on BK is called good if there exists a coloring of each index I in red or blue such that for every pair of indices I less than J, BI greater than BJ. The colors assigned to them are different. So for all the inversions, we want the colors assign them to be different. Okay, for all the inversions pairs, we want the colors assign them to be different. Given a sequence, say compute the number of good sequences of the sequence. We want number of good subsequences, including empty subsequence. Can they be too many? It's one question. I don't think they can be too many. Maybe they can be too many. Okay, let's think a bit. Cases which is n is 300 means we can allowed. It's good mathematically. Solving when it is good. Okay. So if you keep edges from I to j, where bi is I less than j, comma bi greater than bj. If you keep these edges, okay, directed undirected edges, then the coloring of vertices must ensure them to have different colors. What is the message? Is it like my screen gone, or is it like my you're scamming? You have solved these problems already. Otherwise, you have never solved this problem this quick. How are you able to do it on stream? Stream quality is bad. I cannot do anything about that. Predict. Thanks for informing me. I can't do much about that. You guys should adjust with that. Okay. So then the coloring participation should to have different colors means the graph should be bipartite. So we were able to solve what is a subsequence very easily, right? The graph should be bipartite. So this was solved easily. Okay. This is solved easily. I hope I'm correct so far. Why? We are considering all the pairs. Okay. We're considering all the pairs and then we want the graph to be bipartite. If the graph is bipartite, implies that there exists a coloring. But then how many colorings are there? Okay. If the graph is bipartite, if the graph is bipartite, and there is also some property like if this goes to this means all the edges that this has forward it will also have, so it's like a very complicated graph. Not complicated, it has a structure. It's not just the graph additionally has some structure. But yeah, it also has the structure. So if there is an edge from I to j means there is an edge from this to this too. If I write them as directed edges, but if I keep that aside, maybe is this itself is enough. Maybe this itself is enough to solve d1. Maybe this we have to consider a bit for d2. Maybe even for d2 this is not enough. This is not needed. Okay, we have a bipartite graph. Okay. Now we should not have cycle, odd cycle. Is this nothing but not having an odd decreasing sequence? Why? Because of this thing, I think I have once long back have worked about this thing. Okay, if there are inversions, we can always have an odd cycle. I have worked some similar problem long back. Because of that, I was able to write this a bit more, but also because of that, because of this thing. If there is an odd decreasing sequence, odd means then there's definitely an odd cycle. Why? If you use these things, and let's say I comma j comma k is that sequence, there is an edge from I to j, there is an edge from j to k, there is an edge from I to k. So it's an odd cycle. Odd or three length. Okay, now we are here. Now we are here. There cannot be any fucking odd length cycles that goes this like this. Now what's the graph you have? Is this implies and implies? Is this the same problem from last contest, like where we had to count these things? Last problem had like we don't want a decreasing subsequence, right? That was the problem last time. We had to count. But is this enough? I mean, from graphs perspective, this is there, but then it's not just pure graphs because this additional property holds. These are special graphs. If this property is not holding, then we have to think in graphs itself. Why? Because it's as good as a graph. This graph is as good as a general graph or not is what I'm trying to think. But this is not as good as a general graph because these are special graphs, a bit of special graphs. That's why I came back to from graphs to this array. Now if this is not there, then is it possible always is one thing we can think. If there is no three decreasing subsequence, then is it always possible? Then how many edges do we have? How many edges do we have? Okay, okay, will this go otherwise? If there is an odd subsequence, do we get an odd cycle? Do we get an odd length subsequence that's decreasing? Okay, we have a cycle. Consider the first element in that cycle. Now, this we cannot be sure. Let's think a bit. Consider the leftmost thing in that cycle. Okay, it has two edges. It has two edges. Right. Let me think of that. Let me draw that. This has, let's say this is the leftmost in that cycle. I have actually done this work long back. I remember taking a cycle and then doing this work. So it has two edges. If the other two things, because there is a cycle, it has two edges for sure. Okay, odd cycle. So this, if thou, among those two edges, if this is the case, we are done. That means that this is increasing. Let's say without loss of generality, this was the smallest thing. Okay, this is increasing. Okay, but there is an edge from this to this and this to this. Now let's look at these two things. Okay, now if you look at these two things, 1 minute, these both are decreasing, right? Let me draw them well. Okay, these both are decreasing. Okay, now whatever you take here, from this there is an edge, from this there is an edge, and because these are two things, you have some even number of things on this side. From this there is one, from this there is one for sure, if they are not ending. So from this there is one and from this there is one. How do they go? If this one goes down, again we are done. So this one, okay, this can be here also. So this one should be coming above, and this one should also be coming above. And let's say if they are ending now, then it's not possible. At some moment they will end. At some moment, do we have at some moment the next thing being decreasing? Let's look at the last thing. It has two edges, right? Means something is greater than this. Two things are greater than this, two things are less than this. Can we say somehow that we will always have this odd length, three things that are decreasing? Then it comes down to implies and implies the three things are non-decreasing, right? Then it comes down to that. Now we have to count such things where implies and implies three things are non-decreasing. Okay. How do we count them? If that's the case, all the subsequences where three things are, there is no non-decreasing subsequence. Everything is increasing is one thing. Okay, and then only one thing can decrease is one thing. There is no non-decreasing subsequence is what we need. How to prove that there is no non-decreasing subsequence here? So we have two things bigger, right? Okay, let's look at these two itself. Let's look at these two itself. One of them will be increasing, right? The next thing means from here itself, you probably have everything increasing. Can I say that? There is nothing smaller than this. But then if it decreases again, if it decreases, it cannot decrease. But then it can increase and then here it can decrease. But still, it comes back to this. It comes back to this. Means somehow it reduces. Okay, somehow it reduces. I think that's implies and implies. If there is an odd cycle, there is a three length odd cycle. Maybe that's true somehow. If there is an odd cycle, there is a three length odd cycle. Probably it's true somehow, I guess. How to prove that? Maybe taking the maximum. Maximum has two edges, right? Let's look at the maximum. Maximum has two edges, right? Like this and like this. Okay. Maximum has two edges. But then they are like this. But then maximum has two edges and it can only have this them forward. And if those two are not forming something, means they are forming somehow behind edges. Again get connected to this. If they get connected to this, they will. Fuck, I'm not getting it. Have to take some time. Have to think some time. Trolley. Should I read E instead? Fuck. If it is a contest, I would have read E. I need a tissue because I spilled water. I don't even if there are viewers. I can just work on n equals to 5 to conclude this thing, right? For even it's true. Why? Just see this. There are even cycles forming. See, even cycles forming. Even cycles forming. But what about odd? How can odd be impossible? See, for odd, somehow if it goes back and then if it comes to this, that is forming this three length thing, right? If it goes back and then if it comes, that's forming. Like if it goes there or not, it's forming. So probably it forms for odd, okay? Because I'm not able to construct. I can prove it if I think I can prove it, but it's contest, right? I mean, if it's true, we can prove it. I think I have proved such a thing long back. So let me think of now how to not have any three odd length pairs at all. Okay, we don't want odd length subsequence, but then we have to we need. So subsequences that are ending till here, either all increasing means no vertex has something before that's greater than them, or some vertex has some vertex has something before that. I think only this minimum value of such a vertex matters. Maximum value of such a vertex matters, right? To decide if this will fail or pass. If you are including one more element, what matters among all these subsequences, whatever is this maximum value, that's the only thing that matters. Why? When this value comes, when you add this thing to subsequences, okay, two things matters. One is what is the what is the maximum, so that this will be included into that or not. That's one question. Or so you need maximum, and then you need this one also, you need maximum comma this thing. Okay, we need those two things, something that has something greater than or it before it. We need maximum, and then we need this thing, both we need. Why? Then we can get, after you add, what happens if you have maximum and then if you have such a vertex, then you can get what happens after this thing. So if you have this thing, then you cannot add it. If it is less than this, you cannot add that at all, because subsequence fails if you have all these things. So you cannot, it's invalid to add that. So you can update all the counts. You can get all the valid sequences considering this two. By, if you have max comma this state, you can add this and then you can get them. Max comma this. I spent a lot of time on 5 and 3 comma subsequence, right? But maybe some people just guess and go because they cannot prove. I can prove it well because it's odd. I will prove it well somehow. Okay. So now you cannot have less than these two things at all. You cannot have anything less than these two. So that means it will be higher. Means there is no edge from this. If there is an edge from this or this, then we are done. So what was I thinking? All the edges that are there from to this are from previous. All the edges that are there from this to are previous. So that makes us go this or this. So now we have previous edges from this to something previous, from this to something previous. But then we keep going until we have one common thing. When we have one common thing, maybe we again get this subsequence. Maybe it somehow works. When you have that common, maybe it works. I don't know why, but it works. Let's assume that. Let's assume that and then check it if it works on this test case or not. Because if even passes, that's correct, right? And it's easy to brute force. Why? If I have all max comma this thing, if I have all max comma this thing, I can include this and then from all max comma other things. Why? I can update max easily after including this max comma this, and then I can update this thing easily. By, if that is less than this value, it's impossible. I need not even update. But is if this is less than max, then I have to update the second value to max of this after including that. If I don't include that, we have number of count. So if you have max comma this thing, we are done. We are good. So let me keep this as 0 initially, because that's what is good, right? Let me keep that as 0, and max also as 0. When no element is there, let's say this is one possible empty subsequence, we consider it as 0 comma 0. Or I don't know if it's good or wrong, if it's good or bad notation. Or maybe instead of 0, I will just consider for individual thing as m comma 0. Instead of 0 comma 0, m comma 0 means there is nothing. There is nothing that is something less than this. So we have this m comma 0, we have this m comma v, all these states we have. Let's say m comma v means number of things where m is the maximum and v is something that has something before that. None of them can have 3 decreasing sequence. Okay. And this v is the maximum such thing. Okay. If you have these two things, we can update when a new element comes, all the subsequences, right? Let's just have that. So we can solve even. If this guess is right, we can solve even. But this was asked in previous contest also. There was a wrong question where this is not possible. But then there it's not about counting. There it's about checking the validity. Checking the validity. Here it's counting, and we can use O of n cube and O of n square. I should have guessed this. I should have just gone ahead. I wasted a lot of time. I hope I can perform well in this contest. Dun, 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 dun. What are all valid states? dp of val comma 0 or valid, val comma val 2 or valid, okay, max comma 0 or max comma max f, let's say, means it has something before that too. If these are the states I have, I can just initialize them all to 0. So now I have all these possible sets. I have all these possible sets, and then I can show we have these are all sets. These are all sets. Okay, states means sets. M comma V represents a set where all the subsequents are such that M is the maximum and V is the second maximum. Second maximum in the sense it's not the second maximum. Something that has something before that. Okay, M can be here and but this can be the V that had something before that. All such subsequences we are having here. So that's my good understanding. All subsequences are being split into these things now. Okay, all subsequences will be split into these things. Maximum is this. All subsequences will be split into these things disjointly, right? Because any subsequence you take, they have a unique maximum and then they have a unique second maximum. So all subsequences will be split into this disjointly. So initially you have only one subsequence, right, which is a of 0. Is it non-empty subsequences we take, including the empty. So is empty a good one? So is empty is a good one, right? So we don't want to count colorings. We only want to count if it's a good or not. Empty is a good one, but how can I use empty being a good one? Maybe I can just take empty as 0 comma 0 and it's a good one. Initially only empty is there. Let's assume that because empty is possible. Now we can go from I equals to 0, I less than n, I plus plus. And then we have states for int m equals to. So let me copy everything to temp. Okay. So we are very clear in what we are doing. I am very clear in what I am doing. All the good subsequences will be split into these disjoint things. And now I have all the previous disjoint things. And also I have a bijection between. I have a bijection between some set here and some previous set there. Okay, I have a bijection like all these things. If I fix these two things, if I fix this m comma v, I have a bijection of involving this thing. They will go to updated maximum and updated second maximum. That's as simple as that. Okay. So initially not involving this, I'm adding to this, right? And then I will go over all m. Maybe I'll use m equals to 0 too. Okay. All m less than or equals to n, m plus plus, all, what should I call that? Mf, like fucked up maximum. Maybe mf equals to 0, mf less than or equals to n, mf plus plus. So now this is maximum, right? And that is second maximum. If a of I greater than, only greater than matters because equals to is or good edges. If a of I is less than, guys, I am failing on this weird test case which I don't get it right. Because see, I fire to the rain. Okay, this is being weird because value 4 is greater than 2. I should just choose 2 comma 1. Okay, now it's not weird. Now it's not weird. But then, okay, now it's not that weird. You guys can see my screen. What happened was I wrote my own test case 242, but 242 is an invalid test case, and then I was not able to figure out why things are bad. If I see here for 0 comma 02 we have 1, and then we add that to 2 comma 0, so we will have two ones. And once we have two ones, how is it becoming 0? There is something going wrong here. Okay, okay. Temp is this. Why? It's irritating me a lot. If temp is this, DP also should be the same, right? And if DP is the same, why am I not adding them into answer? It's so irritating, right? I don't see it. I don't see it at all. Temp is getting assigned to DP. And then fuck, why am I not able to collect them here? It's too bad. So now I have four. This was the error plus mod and not capital M, MOD capital M. I should not have used M because I generally use mod, capital M instead of mod. Fuck, is that the only error that costed me so much of time? Is that the only error? Plus M instead of mod. Programming is too bad. That's fucking error. See, that means my D1 is right. See how much time I wasted. I wasted time. I got this I comma JNF long back, but then I just was just trying to prove it, or I don't know what I was doing. I should have just proved it little bit. So long time, so long, and then I got solution. Okay, now it's accepted. I think it's still not bad. See, I got solution long ago. So now, how difficult is it to convert this to an optimization? Seems too hard because people thought it's difficult, but we will solve it because I can solve it. Let's hope I can solve it. How difficult can this optimization be now? Because this is the way. Let's say now, how difficult can an n square optimization be? Should I try to change my states into a better one? What all are getting updated here? What all are getting updated? We have to just think. I think it's thinking about where AI falls, right? AI updates all the things, all the states before all the states such that. So if you look at M's here, if you look at M's here, if you look at M's here and MF's here, okay, it's still going on. Contest is still. I cannot judge based on these things. Yeah, it's increasing. It's increasing. So it's an easy problem. It's not too difficult. Contest is still going on. 200 solves at there means it's an easy one. So I can just do it easily. So now for all these things, what do? We are increasing A of I, MF, A of I, M. If you see what is getting updated, if you fucking see what is getting updated, it is it is A of I is getting updated. Means it's either one particular column or one particular row. That's all we need to optimize this D1 to D2. Do you guys see that? Do you guys see that? So we maintain same states, but if you observe here, if you fucking observe here, see, problems are so simple if you try to optimistically look at them. the fact that only one column or one row is getting updated, I need not go over all of these things now. I'll just go over that particular column and that particular row, and then I will find whatever this fucking sum that's going into that particular column. Okay. And then I will find whatever this fucking sum is going into that particular column. Done. Done. Simple. I solved D1. How difficult was D2? Instantaneous. Solve. And I have solved D1 long back. Long back. I don't know. This plus reminder capital M fucked me up, took a lot of time, and then there was no internet, but still this is solved. Problem is solved. Now I just have to think whatever this fucking value is getting added to this thing. And that value doesn't seem too complex, right? It's for each MF, if I can maintain a prefix sum, then I can get this value instantly. I see that I have. So now we have to do prefix sums. Okay. If I have prefix, because here what do I need? Here I want prefix column. Here I want prefix row. Why? Prefix row less than m. Here I want prefix column. All mf's less than this. So we need all prefix rows and we need all prefix columns. So let's say I have prefix rows and prefix columns too. Okay. Let's say I have prefix rows and prefix columns. Int pref row of n plus 1, n plus 1. Okay. And then int pref call of n plus 1 of n plus 1. So this will have all prefix rows and this will have all prefix columns. For plus m has costed me a lot. Then it is all the things that are getting updated are only these things, right? Only these things are getting updated. Whenever, so what do we need? For each we need all such m's quicker, right? And all of them will go to this. So I will first update I will first update temp of arrays. Okay. mf equals to 0, mf less than or equals to n, mf plus plus. I'll update this shit. Okay. Temp of ai of mf plus equals to pref row of, because this is a rows prefix sum, right? Because row is varying, column is fixed, so this is a columns prefix sum, right? Pref call of column is mf and then this is m. We are done. If I have the prefix sum, I'm done, because that prefix sum is what is getting added. A of I, not m. Why? All the m's that are going into this are like from less than or equals to m, right? That's it. That's it. We are done. So now we have, I won't even maintain temp. Okay. I will update DP directly. So now I have to be a bit careful. I have to be a bit careful. Okay. All these things have been added to them. Also, all these things I have to add now. Skinhead, everybody. It's pref row. See, you guys don't know how to use prefix sums. Even if you have solved D1, you guys might not have sums, and then you guys worry about what topics do I. What the fuck was that? Try to use what you already know. Okay, if this gets solved, I will mock more. Okay, so now instead of doing this 2D, we're able to do whatever this code does. I think ChatGPT can do this optimization from here to here. Maybe it can't. Maybe it can. I don't know. It probably can't because this is a different array and this is a different array, right? So now where are we? These are the only things that are getting updated. Now, what does pref call have? It has prefix arrays of all that column. That's it. What does pref row has? It has prefix row of all those columns. And now what all are getting updated? Only this column is getting updated. Only this row is getting updated. And it's not that difficult to just update that shit now, right? To recompute that shit. I will recompute that column again. I will row again. And I'm done. And I'm good. Done. O of M, O of N, whatever it is. So how to compute pref of all rows? Row equals to 0, row less than or equals to n, row plus plus. Okay. Pref row of of 0 equals to dp of of 0 for int c equals to 1, c less than or equals to n, c plus plus. Pref row of uh, of c equals to pref row of of c minus 1 plus dp of of c mod modulo. But I'm not taking modulo because it's just one initially, but it's a good practice to take modulo, but light. Simple coding. Coding is not too difficult, guys. Problems are being so fucking direct. Like, do I enjoy this thing? No, right? What was this? Simple guess, done. And then stupid brute force. There is no good idea at all. Brute force. And then what? Observing the fact that there is only one column and one row getting updated. Stupid problems. I don't even have fun in this. That's why I like solving much difficult problems. Talking too much with my low rating. I get that. I'm not taking modulo here, but here we have to take modulo. Now I have to recompute that thing. Okay, I have to recompute that row or column, whatever it is. So what we have to recompute? I should not update here because if I update the row here, then what happens is I'm using that row here. So after both of this, I have to update. Okay, whatever the row that's getting updated is. So we have to worry. Should I try to consider the intersection thing? No. Why? This row is just prefix sum of this row. This column is just prefix sum of this column. This column is getting updated. This row is getting updated. Just compute them again. Simple. What row is getting updated? M. Right. M. M. Now I have to put modulo because I have to be careful. I kept M again because I use M a lot. Only this row and these columns are getting updated. So recompute there. Shit. Okay. It's not that difficult. So this is definitely correct now. Why? Because the previous shit is right. So this shit also should be right, right? Unless I write some errors. Oh, 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 oh. Sitting up. Mm, 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 mm. What? M is A of I. No, I cannot change that. I'll just keep in M equals to A of I. MF equals to A of I. Stupid programming. Or should I keep val and replace them everywhere? Why? Let me just make sure it's correct first. I should not have removed the commented code, right? D2 are pretty direct. Because it's difficult to solve directly D2, they gave div1 so that we can notice that the column is being same and then we use it for div2. So they are helping us a lot. And then you guys will get scared of, even though they are trying to help a lot, should not be like that. dp of m of mf. Mf, if you fix mf, dp of phi of I is pref column summation of dp, the old dp, as long as m is less than or equals to a of I. This summation is as long as mf is less than or equals to a of I. And then this m is getting, this a of I is getting fixed. Sometimes higher, sometimes lower, sometimes lower. What is that? What's going wrong? Only this row is getting updated, right? Only this row is getting updated. Wait, if this row is getting updated with this column, this row is getting updated with this whole columns where m is varying, mf is constant. So am I doing this thing correct? Am I doing this process? Am I doing modulo correct? Why am I making stupid, silly mistakes? I truly don't understand that. Shitty problem, and then I cannot even do that correctly. Okay, I'll just debug this thing again. 7 the answer. No, what's going wrong? DP seems, ref call seems right. Should also be right. Right. So now I will output here maybe things same. After one update. After one update, what happened? This both got added. Is this correct? After 2, what happens? Or after 2, what happens? dp of 0 comma 2, which is, it should be 0, right? dp of 0 comma 2 should be 0, right? Why? What does dp of 0 comma 2 means? Maximum is 0, and wait, how does this not equals to this mathematically? Right, if I see here very clearly, a of I mf is getting updated every time with dp of m of f. If I fix mf, m comes summation m comes here, summation m from 0 to m less than or equals to ai is nothing but that summation. If okay, I'm doing right, everything right, I don't get it. Here m is maximum. Okay, fuck, else if, right? Else if a of I, okay, this is true. This is else if a of I is from MF to capital less than capital M. Yeah, I should have been careful. So this summation doesn't cover everything. This summation is else if. See how carefulness is important and not topics. Okay. Wait a minute. Now again. This should only be updated for m greater than a of I. So it's just simple. 4. Yeah, we are done. We're done with A2 just like that. Let me run this fucking first fucking sample. If it runs, we are done. Now let's verify if I've done everything right. For this, fixed AI comma MF, for this thing, what's getting added? All the M such that M is less than or equals to A of I will get added to that, right? Directly comes here and that gets added. So that's obvious. All the M less than or equals to that will get added. All the M less than or equals to AI will get added to that thing. That's correct. Now if you look at this thing, this seems right. This doesn't seem wrong. If it is later, it cannot affect the other thing, MF, right? Why am I wrong now again? Reminder modulo n is why I am wrong again. Am I using that elsewhere? Don't be like me, guys. Just solving problems is not enough. Do you see? Or I'm scared that I cannot do E. That's why I'm doing this shit on D2. Maybe that's the reason. Right. Asking already, has Teja done E already? And then I'm stuck here. I don't know why I'm doing this to myself. Pref row, pref column is right. And I'm taking pref row, pref column for those things. Yeah, I'm taking. Okay, 1 minute, 1 minute, 1 minute, 1 minute. If this row changes, all the other columns changes, right? Okay, that's why it's a bit more difficult. If this row and this column changes, that adds something to all the pref rows. That adds something. That adds something. Inga hell Hitler. That adds something. Okay. If a row and a column gets updated, that changes other rows, other pref rows and pref columns. If this column is getting updated and if this row is getting updated, how does other pref rows changes? They get from here some addition. Okay, they get some addition from here. So whatever the update that has been happened, we have to do some range update now. So we have to do range update. We have to do range update. We want prefix sum point update. Probably not that easy with this thing. It may be easy, but not that easy. Can it be easy? Maybe not. Can it be easy? Can it be easy? I don't know how to use multiple Fenwick trees. How to use multiple Fenwick trees? Can we even use that? Will it even compile? When this row gets updated and this column gets updated, for all these prefix columns, I have to change all these values. So that's not that easy, right? That's not that easy. But if I have Fenwick trees, I change those elements, right? And then I'll be good. Nigga, hell Hitler. So let me change the code. I'll assume that I don't know how to initialize these things now. ChatGPT, can I ask it? Let me assume somehow I initialize them, okay? Let me assume I initialize them. So now we have those Fenwick trees, right? We have those Fenwick trees. So if we have Fenwick trees, what should I do when I have 0 comma 0? I will just update Fenwick tree is same for each rows. Okay, Fenwick tree is same for each rows. Fenwick tree will just have this. Okay, ref row of 0 of 0 dot add of 1. That's it. Okay, ref call of 0 of 0 dot add of 1. Row is different, column is different, entirely two different data structures. Now to get this summation, what can I just do? What can I just do to just get this summation? A of I of m of, right? It's pref call, right? So I'll do pref call of what? What's the column? MF. A of I is the column. Sorry, MF is the column. And what is the summation I need? Till A of I is the summation I need, right? Till A of I is the summation I need. And then what would I do? This shit is what I'm adding, right? So int add equals to, this is what I'm adding to, that's what I'm adding this index, right? I'm adding that to this index. So what do? I will again update in the same similar fashion, pref row of, to what it's getting added. What row is it? A of I row, right? Dot add of, what's the column am I adding? 0 comma 1, 0 comma 1. So we are just trying to add wherever we are adding it. Mf comma 1, add. How to do modulo 2, because these summations are a bit modulo, right? Maybe people use mint, fast coders. I'm a loser, that's why I won't use them. Where are we now? I'm adding that whatever the addition, that this was the addition to this point. So I'm updating that addition, and then I will update pref call of mf of a of I, sorry, mf dot add of. So this column again, that much got added at this point, right? So point update prefix sum. Convictory does that for us. Same thing is what I'll do here. Int add equals to pref row of, what's the row? M. And what's the sum we need? Till a of I. And then what do? I update both rows and columns, because this row is this much at position add. This is getting add at position M. So we are done. We are doing point updates, prefix sum using Fenwick tree. Would this work? If company sees this, they would not hire me, I think. It's compiling and we're getting wrong answer. That's fine. That's better. That's better. That's improvement, right? Stay, guys. We can do this problem. Stay. Don't leave the stream. We can do this, and then I'll try E2. Okay. But fuck it. Why am I not able to solve this thing? So easy thing. So for we have rows, we have n Fenwick arrays. We are updating a point. We want a summation range, right? This is the update that happened to this point, and then I have updated that in both the row and the column. Row and the column. So print them and see. Okay, here itself we are going wrong. So we can verify this thing. What's happening here? After 2, should this get activated? Wait. I can't say if my mind's even here or not, right? If I'm making such mistakes. Where's my mind? What am I thinking? You know, guys, today I today I said I will not, I will take a leave. I want a leave. I've been working too hard all nights. So I have asked her like I wanted this. They're just bad. So I've solved the problems. What's this error? What are these errors? 200 solves doesn't mean that's a difficult problem. So let me try in 15 minutes. We can do that. You're given a bracket string s of length n. You can apply the following operations arbitrary number of times and in any order. Choose an index size such that s plus 1 equals to this and replace both of them with this. So it's nice. Both this will become both this. Okay. Choose an index this and then replace both this with this. Okay, this is the operation. Find a regular bracket sequence T that can be obtained from S by applying any number of operations up described above or print minus 1 if there is no such T. So it's a nice problem. Should S not be equals to T? What's the problem? We have an S. We want to find a regular bracket sequence T. Okay, we have some bracket sequence S. We want can be obtained by using the operations. What are the operations? S. Okay, where you can do this and where you can do this to this. Okay, what's happening in the operation? You have to see what's happening in the operation, what remains fixed, what's happening exactly. You have to see that very clearly. Okay, number of open, parity of open remains same. Okay, so if you don't have a same parity of open, you are cooked. Okay, if you don't have that, you cannot do anything. So that's one thing you can say. What are the necessary and sufficient conditions is what we have to look for. And once we know the necessary and sufficient conditions, maybe then we can think of what's the bracket sequence that we can obtain or not using just this operation. So we have to still say more about operation. I don't think this is all enough. Just parity is not enough. Maybe it's not sometimes, because if all you have is this, then you cannot do anything, right? If there are no adjacent things, you can that things that are same, you can't do much. And let's see something like this, something where okay, if I try to see them as 0 comma 1s, like this comma this, so if these two are same, I will see this array as 0. If these two are same, I'll see that array as 0. How does this change? Because we are changing this, we are changing this XOR previous one, so we are changing one here, we are not changing this, we are changing two values. Okay, so seeing that doesn't mean changing two values. I'm trying to see in terms of this. I'll try to see XOR of these two things. Means XOR of these two things. Then this value doesn't change because XOR is same. And then but these two will change, and then these two will change. So it's like two non-adjacent things will get flipped. Okay. But then does regular bracket sequence have something nice in their XOR? I don't think so. So let's not look at that. And then what can we do? Look at. So won't you kiss me on the mouth and love me like a sailor when you got it edge? So if there are no adjacent same things, we can't do anything. If adjacent same things are there, all of them can be converted into. So it doesn't matter. The odd ones matter, right? Even things can be just flipped. Even things can just be flipped. Okay. Always even things can be flipped. So how do we see this now? How do we see this? If none of them are, if none of them are adjacent, means it's like this, it's like entirely alternating, then we can't do much. But if there is something, sometimes it's impossible, sometimes it's possible, but then if there is something that matches on both sides, and also we know that parity of this and that are already equal, parity of opens and closed are already equal. Okay, so this can be an example of parities of open and closed being equal. So now what can I do? What can I do? And these two do closed. I need some good observation. What the fuck is happening? I need some good. I get it. I will keep a dot here and then I'll write stuff. See? Want. So and then I will just flip like this. And then I can just maybe flip like, okay, 1 minute. And then I can probably flip these two like this. And then I'll probably flip these two like this. So is it always possible if it matches? We can think of that. Okay. Is it always possible if it just matches, if the parity matches? Is it always possible if the parity matches and then there is something that is same? Okay, let's try to think of that. Let's say these two are equal. Okay, if these two are equal, I will flip them and then I'll connect all of them. Okay, if I connect all of them, so it's like we have, so some two are equal. Okay, I will see this if them to this thing. So now these three are equal. Okay, and now, but then parity also depends, right? Can I always keep them even? So let's say, can I always keep them even? That's one question now again. Can I always keep merging them? Can I always keep them even? It's one question now. So how much can I keep merging? How much can I keep equal, right? So If you have it, because these operations are reversible too, right? So that must be like an relation between this and something else. Can I always convert? This is one other question I can think of, right? Can I always convert this? Okay, that is bad one. Can I always convert this to this? Is a question we can think of, right? This question we can think of. How can we do that? Is there something that restricts us? Is there something that restricts us? Is also we can think of, right? We have to give more importance to operation. Maybe we can say something better about the operation, right? That is always the goal. We have to say something better about the operation, and then only we can solve the problem. Can I convert this to this? These are just some cases I'm unnecessarily working on. Okay, this can be converted into this and this. Okay, and then maybe I can convert these things to like this. Okay, but what is restricting here? What is restricting this summation? Somehow the number of odd things are odd here. And then, so let's say, let's look at the prefix array of open odd things. Okay, what happens after an array? One odd thing will get disappeared and one even prefix thing will get added, right? This prefix array parity will get added and this prefix array parity will be gone. Both of them are odd. There is something we can say probably. Okay, let's think a bit. Maybe flip this to. I'm not thinking. I'm absolutely not thinking. I have to think well instead of trying randomly. Okay, it's not happening. I'm just coming back. Sure. But what is restricting? If you find that out, if you just find what exactly is restricting, then itself we can probably solve the problem. Problems are that direct. Observe that. Okay, definitely something is restricting me to go from here to here. What is that? What is that that's restricting me? Because if you can flip that and then you can maybe merge this, but then you're always having you're always having this odd thing, this initial odd thing, right? This initial odd thing is always there. You cannot make it disappear with your operations, right? That initial odd thing, you cannot change number of things before this. Okay, yeah. For this thing, you cannot change parity of this things before it, right? For any closing thing, you cannot change parity of this thing before it. Why? You have some closing things here. Their parity will not change. You have some. So under this operation, for any this parity of before it or same goes for any this parity of before or after. I think before or after are both same, right? Because total parity is anyway matching. I'll write after it or same. This cannot be fixed. These things must be fixed. Okay, so now if for some this, if there exists odd number of, I think I need not even look at this. Probably this is sufficient for this too, right? Maybe that's sufficient for this too, maybe. So now for some this, if there exists odd number of this before it, see, it's always about looking the operation in a better way. What can you say about the operation a bit more? Because you guys should give logically, if there is a simple proof, everything can to come from here, right? You have to see the operation and then come from here. I was able to see here itself that, okay, why can't I go here? Because here before this there are even number of things, but then here before that there are odd number of things. Then we can absolutely say that for any closing bracket, suddenly two things are just getting spawned from somewhere. So number of open things will not change, and even for these new things it's true again.
Am I back? Arpit Kumar. It's really irritating, right? Like I put so much effort and then I try to do that, but then it's gone. What the fuck is that? So guys, I will go brief again what I was doing. So I wrote all these things. So I tried something random. Okay. I tried something random. But then I came back to seeing because operations are reversible. As I have explained. Oh, I'm not showing my screen. Fine. I explained well, I think that's good enough. I told we are splitting all cases into M comma MF. You have to see it multiple times. I think I have done it good. Not too good, but I have done it a bit good. So what I was saying was because the operations are reversible, there is an equivalence class. You have to see it again, Arpit. D was explained well. D was explained even with diagrams, right? I told all the any good configuration can be classified based on its maximum, and when you're adding second new element, it's maximum and something that has something before that. Only these because if something that has something before that, then that will affect this thing, right, into a bad sequence. So if we maintain these two, we are good, because any good sequence can have just some maximum and some other thing which has a before below maximum. Only those two things matters. So I'm grouping, I'm disjointly based on that m and this m comma mf. After splitting them, we can add one more element and then we can again get the new m comma mfs, because if this is greater than this, m itself changes. If this is here, we get a new mf. This would be a new mf. What is mf? Something bigger than something before, and this value is maximum. That is mf. Okay. Think slowly, try a bit. It just comes directly from writing DP. Tried randomly. I have tried randomly on opening, closing, little again because my internet has gone and I don't know where it has gone. It again. One thing we can say about operation is operations are reversible. Operations are reversible means you have to think what all are possible, right? Because I have already told you many times reversible operations form equivalence class, right? Reversible. Pradeep Kya, please try to follow me. Okay. Uh, See, the thing is, you have to become very, very clear in terms of solution first. Very, very clear. We have these disjoint things, and then we are updating, and then you will become better problem by problem. Okay, if you cannot implement right away, even leave it. Maybe go for smaller DP problems. Maybe solve much more DP problems. Maybe then come back. I think this is a simple one. It's just DP brute force. But maybe the way I wrote was not that simple. Okay. So because there is an equivalence class, first I tried something random. I tried maybe this is there, that is there, and on. But then I thought, okay, if it is an equivalence class, why can't I try to understand the equivalence class itself, right? Because it's an equivalence class. It permits few things, it doesn't permit few things. Like into that class, because I told what's an equivalence class already. I cannot keep explaining the same things again and again, even though I want to explain. So now I'm thinking, what is the equivalence class of something? Then I can say any even things. Okay, I was telling any even things, like if you have two zeros, you can move them. You can move them to the start, right? Two zeros can be made two ones, and then you have you have forward. So you can always make them forward, and then you have this thing as some odd components. So now you have to think, are these things unattainable? Or these things can you never do anything about them? You have to think. So are you understanding, Pradeep Kaur? Is there Ravi? He's not there. I'll tag him or what? So you get me right. So before getting scared, before doing random things, I think if I have looked at equivalence class, maybe I would have solved this problem in the 14 minutes I had in the contest. So following good steps is very much better. Do you see? If you look at this equivalence class, it says, okay, now some odd components are being left out, right? If this component was odd initially itself, you cannot do anything. So now think of odd component. Odd component. What's an odd component? If you see zeros, guys, whoever asks me shitty doubts, first pay attention to whatever I am saying, because even that has some value, right? Not just your question, right? Now done basics BB and STR, and I'm only able to do till B. Only able to do, if you say that to yourself, you'll do till there only. Sometimes if it doesn't have DP, if it doesn't have DP, even that's what you're telling to yourself, or any other data structure. What the fucking data structure does today's C have? Does today D1 have? I don't think they have any. You have to try more. You have to really think about the assumptions that you are telling to me, or the assumptions that you're telling to yourself. You should not, before making any assumptions to yourself, you have to rethink a lot. You have to try a lot, and then you have to conclude them. Okay, it should not be like this. You have to really think if they're true or not. Okay, whatever the assumptions you're making on yourself, you have to, unless you try, you don't know whatever the shit it is. Okay, so try more, see things for what they are. Okay, solve a problem and observe things better. See my streams and see, like, realize that they're not having anything. So do you agree that, okay, now let's look at odd component. Can you reduce or make some odd component disappear? No, you can't, right? If you have odd number of zeros with these operations, even if you change something middle, one side will be even and the other side will be odd. Odd will always persist. So you can never ever remove this odd component of one. You can never ever remove this odd component of zero. Do you see this, Pradeep? So because this odd components persist, means if you have an odd component, whatever you do, that odd component persists. It can never go back. Okay, because changing even number of adjacent things in an odd component will make either this side even odd or this side odd. So odd components always persist. So whatever you do, there is an odd one here. Whatever you do, there is an odd zero after that. After that, there is an odd zero, because odd component, the this sequence of odd components persist. You can never. So if you have one odd component and then one odd component of zero, odd component of one, odd component of zero, odd component of one, odd component of zero, they persist. Whatever you do, you cannot avoid them. Maybe you can make them like this. Maybe you can make them like this. But then they persist. Why? Change two things. Change two things from this odd component. You still have an odd component on here. So those things persist, like they never go away. Like the odd components, they never go away. So this will always exist. So that makes the equivalence class complete. What's an equivalence class? Even length comma 101. This is an equivalence class. So even length comma 1001. So these odd components, whatever are persisting, those are the things that decide. Do you get this equivalence class? Guys, Arpit seems to have gotten. Pradeep Kayar, have you gotten that? See, I have explained this in div 3c or div 3d. I have used equivalence class reversible in some div 3c, and even in div 2a, it's the same thing that's helping us. But there is more work, there is more hope, there is more try. You guys don't realize this, and then you guys say, okay, if there is some data structure, I can solve it. Okay, zeros. It's all zeros, because I'm trying to move two zeros to front as much as possible. As long as there are two adjacent zeros or ones, I am moving them forward. Okay, then we can come here. I told you, when there is an equivalence class, we can move to some extreme point, and then we can think of that. If that extreme point defines the whole set, means any of them can come to that extreme point and then they can go back to. Okay, this is a simple idea, but this is an intentional idea. It's not like my intuition, or it's not like I get a brilliant idea. It's a well-known fact that we do in even in easy problems if you guys prove well. So even length is just set of zeros or ones. And under this operation, the subsequence of odd components persists. Do you get what I mean by persists? Like they can never be gone. Means what all you can achieve is this, inserting some even lengths in between. So what all you can achieve is you have 1 0 1 0 1 1, and then you can insert some even lengths. But because parity of even and parity of ones equals to parity of zeros, you will always have something like this. Because parity of ones equals to parity of odd, you will always have something like this. Okay, so you always have something like this. Okay, if this sheet is, if this one, then then that will persist. This will persist in some cases. Okay, in some cases this will persist, in some cases this will persist. This is nothing but 1 0 1 0 1 1 0 1 0, because I have already told parity of zeros and parity of ones also remains constant, right? Persist is nothing but invariant. Again, it's an invariant. You will always have an odd component. You will always have an odd component, and you will always have an odd length. Sorry, uh, let's let this length be L. You will always have a subsequence of alternating odd components. Okay, not even components. So you will have subsequence of components. Okay, of length L always. So this subsequence is not formed after taking a subsequence. You will take the odd component as a subsequence. You will take the other odd component as a subsequence. So whatever you do, this one's odd component subsequence will always persist. You can take that. And then this zero's odd component will always persist. You can take that. But if this is always persisting, then you have everything that is possible. So these things will never go away. And then other things you can move as you like. But then you can only have add even things here. So what do you add? So if remaining even length is, if remaining even length is uh if remaining even length is 4 multiple, then you can always add them as two things here, two things here, because you can move them as you like, right? So if it is 4 multiple, here 0 or 4 multiple words. But you can see in other cases whatever you do, you cannot you cannot help in other cases. Whatever you do, you cannot help in other cases, right? Is that right? So what all can you do with some even length? You have some even length, all ones or all zeros. What all can you do? Maybe you can do it like that, maybe you can do it like that, or so. But I don't think these things will help, right? You can move even lengths across. You can move even lengths across. Let's say you have some even length here. Finally, you have some even length here, and then some even length after this thing. Okay, now this even length, maybe you can make it, even if it's two multiple. I'm just thinking about two multiples. Okay, I'm sure if it's four multiple, it's done. If it's four multiple, I can just keep even things here and odd things here, done. If it's four multiple, done. Here, if it's zero, then impossible. Else four multiple, done. Okay, because I can keep them perfectly. So now let me think of even, but not four multiple. Here I can make them like this, but then here is what we have. 4. Can I flip Two things. I can only flip two things, right? I can only flip two things. I can only flip two. Now think of that. Why an even thing is not possible? Now think of that. That other than fixed odd ones, if you look at even things, what happens? If you look at even things, their values changes by two. Two of these things become two of that things, right? That's what happens, because these things persist, they never go away, they always exist. Now if you see the remaining things, because this frequency is always fixed, if you see the frequency of other things, if you see the frequency of other things, what is happening? If you have six, if you have six, it is it is 2 times 3 comma 0, right? 2 times 3 comma 0, and whatever you do, this will become like this and then this will become like this, but you can never make them equal. Okay, you have the sum equal, but then you can never make them equal. Why? One is odd and one is even, so whenever it is two multiple, it's impossible. I'm not even proving it only for the before even lengths, I'm proving it for general case. Why? Take general case, this frequency of odd things always exist, they never go away. Okay, so they always existed. And then what have you done after an operation? You have changed frequencies of odd things, removing these things aside. Maybe you have changed them by 2. Minus 2 happened here, plus 2 happened here. Keeping these things aside, that proves that you can never make these things equal, right? Do you guys get it? How I am proving perfectly? I'm not even proving for just the before things. I'm proving it for everything. Yeah, something like that, because it's not easy to look at them, right? When they are just zeros and ones, it's not easy to look at them, right? What I mean is, if whatever the even length that's before, Ravi, you came late, right? What I'm trying to do was, I'm trying to look at the equivalence class, because if it's a, because see, because reversible operation, there is definitely an equivalence class. I'm trying to first understand that class, and once if I can understand that class, then I can think of this problem. So it is just structured in two ways. If you guys follow my rules, whenever you are reversible, there are equivalence classes, and then we can look for invariance. I told one invariant is all obviously parity of opens, parity of closes doesn't change at all, parity of zeros, parity of ones. Then we can go to an extreme case whenever equivalence classes are there. I have even told that extreme case can be this thing. Whenever you find two adjacent things, move them forward. Whenever you find adjacent things, move them forward. Now you have these things. What are these odd components? And they persist over all operations, is what I proved here. They persist over all operations. In fact, this is an invariant. There is always a subsequence of alternating odd length components. This will always persist under this thing. So the best you can do is that. And then let's think of that. From the previous problem, number of zeros and number of ones are equal, parity of them equal. So that's why we will have same number of zeros, same number of ones. So now we have two different possibilities. One is 0101 or 1010, two different possibilities, right? If you look at those two different possibilities, one is, where did I write that? One is this thing, the other one is this thing. Okay, this thing, if the even length is 0 or 4 multiple, it works. Now I'm thinking, if it is just a 2 multiple but not a 4 multiple, then is it impossible, is what I'm thinking. Then is it impossible, is what I'm thinking. If I think that, I'm trying to see based on the frequencies, because if we can never make these frequencies equal, that's the restriction, right? If we can never make these frequencies equal at all. So for that, to prove that, what I'm doing is, these things always exist. Okay, so look at frequencies of even comma odd, zeros comma ones, by keeping them aside. Keep them aside, because they always exist. Keep them aside. Now look at frequencies of even comma odd. What happened after an operation? Two things from here became two things from here, right? So if I take the two common, what happened to the frequency of other things? One thing went from here to here, right? One thing went from here to here. So that is 2 minus 1. So they can never be equal. They can never be equal. Do you guys see that? So whenever it's 2 multiple, it's impossible. I proved that easily just using the frequency argument. Just using the fact that these frequencies always persist. Keep them aside. Look at these things. After an operation, two things are changing. So they can never be equal. So So the problem is perfectly done. It's done and simple. In this case, 0 impossible, 4 multiples done. In this case, so problems can be very simple. Once you solve them logically, implementations can be very simple, and still the problem can be difficult because we have to be very careful. In this case, 0 is not possible. 4 multiple done. 2 multiples not possible in both the cases because you cannot even make the frequencies equal. Right? So it requires clarity. If you have clarity, implementations are simple. Are simple, proofs are simple, implementations are simple. I have done solution, I have done proof, I will do implementation too, right? And I don't even care about these things. I will first convert them to this, whatever the odd components are. Okay. If I maintain a stack, it's better. If I maintain a stack of even comma odds, why? Why I'm maintaining a stack? Because odd component, even zeros, odd ones, odd zeros. All of this can be combined to even. How? I will eliminate this one. And then if I have this thing in the stack, I can make this and this combine and then I can remove them also from stack. So I will try to form this stack. Okay, do you get it? I will try to form this stack. Okay, I'll try to form this stack. See, implementations can be cool. Implementations can be simple. You guys can get this kind of content anywhere. Whatever the courses you buy, they are all cheap, cheap content. I would value them as low because I would value them as negative because teaching wrong ways is bad, right? Teaching wrong ways is bad. If they teach you in a way like, okay, you have to learn this topic and then you solve this, how the fuck can you improve? You always stay in that doubt, right? Maybe it's a topic I don't know. How can you overcome that? If you use some things like basic things like equivalence classes, sets for dp, bijection for dp, equivalence classes for an operation, invariance for an operation, parity of even is invariant, parity of odd is invariant, these are very basic math topics that exist everywhere. Like these are very basic math topics. These are the topics you guys should be well aware of. Okay, if you take some course, they don't know why they are solving. They can solve, but they don't know why they are solving. They don't have the clarity. Okay, people can be better than me, but they may not have that clarity. Like not better, maybe closer to me, but they may not have that. I am talking about like whoever sells courses, let's say, because I'm not selling yet, right? So now I'll maintain a stack. I'll maintain a stack, car itself. Why not? Okay. See this beautiful implementation. If this s dot empty off, then see sometimes sometimes there are questions. If you can maintain such a stack, the problem is done. There was one such question. When I have solved it, I immediately knew like that. Else if s dot top off not equals to s dot, see, s dot pop off, else s dot push off, see, whatever this end odd shitty thing is, because we are removing even things, we are removing two things at a time and this works perfectly. Okay, so now the answer, int rem equals to n minus s dot size of, right? If this size, if rem reminder 2, reminder 4 equals to 2, one thing is very clear. Okay, if s dot size of reminder 2 is odd, or because if this size itself is odd, then parity of ones and zeros itself are not equal, right? Then that's bad immediately. And if that is even, then even if this rem reminder 4 equals to 2, because now we know this is even, probably n is also even. If this is even, n is also even, if because we have removed even number of things from here, right? So n and parity of s dot size are always equal, so rem is always even. Because rem is always even, because this this eliminates any even n odd case also. Okay, rem is always even, so with respect to 4, if it is 2, it's impossible because we cannot make number of zeros equals to number of 2's, keeping these things aside. Okay, else if rem equals to 0, else I'll just separate 0 case. Okay, if rem equals to 0, okay, I will just write else case itself, maybe written. In the else case, if rem equals to 0 and s dot top of equals to this shit, then again minus 1, because s dot top of was ending wrongly. We have see, implementations can be simple. You guys need not think some e means it has everything. Problems can be difficult just because they have more because you actually have to solve them. Random guesses cannot work right here. Frequencies, you have to show that frequencies doesn't work and all. So with some conditions itself problems can be difficult. I have solved so many problems, right? Else it's possible. Else what do I do? For int I equals to 0, I less than rem by 2, I plus plus. This is an even number. Okay. Should I make it vector? I don't like that. But I have to reverse it. Okay, I have size, right? What topics do you fucking need to solve this problem? I don't know topics, I don't know data structure. Unless if it involves a data structure, I can solve this thing. You guys don't try hard enough. Just admit that. Okay, you guys don't try hard enough. If you try hard enough, see, I gave a book mathematical circles. Try out mathematical circles, okay? Yeah, I have to sleep, bro. It's 1:42. Fuck, I want to stop at 12 or something. I have to sleep work. I'm looking to shift company too. I have to do that too. It's done. There's nothing more left. Why is this possible? See, answer. Why? Because I solved because I solved it correct. Something is not reachable, it seems. Let's look at that. I fucked up. I fucked up. See, I solved everything well, but then why do I make wrong answer? Because in this case, in this case, in this case, I cannot change that to open. I have to keep it closed, right? I solved everything, and then why do I do this? So I have to start with, if I is 0, I have to start with, this is s dot top, right? I have to start with, yeah, I made a mistake there. Okay. So now I have updated that. Now I'm considering what is the stack character. Because to make stack work, I made this condition, right? Rem 0 I eliminated because to make stack work. See, being so careful in the solution and then in implementing, I have to be even more careful, right? I don't know why I have done that. Like, why I do that so often too, I don't know. Right? Maybe we can just check it. Okay. 1, 6, open, maybe 8. Okay, 6 is fine. close, open, close, open. So this should give -1, right? And then if I make it 8, and then if I add two things here, that will give this. But then even with 10, if I extend the stack, if I extend the stack to this, it's giving that correct answer. Why? This is the odd thing, right? But then we have this, it's giving right now. So that's the only mistake I made. That's too sad, right? After solving everything, making such a stupid mistake is too sad. But I'm used to them because I can do so well and still I make mistakes. See, accepted. This should have happened here if I was a bit more careful. 415 solves. It's too easy problem, I think, because it's an easy problem, right? This is a very standard one. Hope it's a standard one. I can't do this now. I have to sleep. Guys, good night. I'm sleeping. I should change job and quit CP. Yeah, got it, currently. I just want parity, bro. That's why I'm maintaining it. Okay, maybe lead code thing, but then it's not needed to. It's not needed to. Okay, because why I want that was I want to merge previous odd to this odd. That's why I maintain that. Okay, because see, odd ones, odd zeros. If there are odd ones, see just for this case, odd ones, even zeros, odd ones. I have to remove these things and then I have to merge these two and remove, right? So if you have a stack, I can remove these things nicely and then I can remove these things too. In that way, we can keep removing and then we can add actual ones finally. That's why stack is good here. It's a basic one only. Yeah, stack one is a basic one only. I mean, you have to think for better, cleaner implementation, maybe. This is the best example for stack, I guess, right? But then guessing it is easy, I guess. Because this structure is so common, I unnecessarily complicated it a bit. Once we know the structure, 4 even is seemingly bad. But then I proved it much more clear. I told keep the frequency aside, then you can see this frequency cannot match. But that's also not that difficult to see. I proved that the subsequence remains same. That's why I kept more effort, I guess. If it was a contest, could I have seen that well or quicker? I don't know. Maybe I have seen it quicker. I re-explain things many times because the internet keeps going. I'm leaving. Okay. Should I solve? Should I solve the perfect matching one? Can I solve it? Can I solve it? No. It's Code Chef. Before this, I was trying to look at perfect matchings. Somewhere here. Somewhere in the universe, somewhere someone got us. Wish that made it easier. The old smallest violin really needs an audience. So if I do not find somebody soon, I'll blow up into smithereens and push my tiny symphony all up and down a city while trying to put my mind in his like finishing this melody. This feels like a necessity, so this could be the death of me. So what I told was, I told few things, and then, so we want to count number of perfect matching trees. Okay, number of trees that has a perfect matching. I explained this in the starting of the video, so I think it makes sense to end with it. Okay, so once you remove this, there will be even components. All of this should be even components, and only one can be odd. Only one can be odd component. Okay, all of them should. That's a necessary condition for a perfect matching. Why? Because maybe perfect matching has uh, this and this odd component as an edge, and all of them should form perfect matching among themselves, right? So this should be even, everything else should be even, so only one must be odd. Why? There should be an edge to that, and then that forms a perfect matching, and this forms, right? So size of those component must be happening. So what I will do is, I will brute force this set. I will brute force this set. Okay, do you get it? Do you guys get it at least at a high level? Do you guys get it at a high level? What I'm trying to do here? And then we have to count number of perfect matchings. Okay, given that trees follow this ordering of one will be the topmost, trees follow the ordering of one will be the topmost, and then 2 3 will attach to smaller things, kind of. Okay, so I will brute force on this set. Okay, if I brute force on this set size, let that size be z, odd length size z. Okay, this size be z. Now what? Now we have the remaining things forming a perfect matching, smaller size, forming a perfect matching by leaving one top thing aside. Okay, by leaving one top thing aside, by leaving one top thing aside. So in that way we can find that. But now you have to find what are the number of ways by leaving one top thing aside where everything being even, all of these things are even, only one top thing, because that happens truly. Because if this is odd, all this should be, I mean, when you go down from here, this will go to top, right? And then all of this should be forming perfect matchings among themselves. For that reason, when this is odd, what does it mean? Without using parent, what number of things, all of them forming perfect matchings. So how to do this thing? How to do this thing? It's nothing but perfect matchings of some even sizes getting multiplied, right? So some even sizes splitting, and then they are getting multiplied. So how to find this thing? Maybe I can brute force on some particular value. Okay, maybe I can brute force on some particular value and then do this. I mean, we want many even groups forming, and then we want their value. If I can get this one, then I can get for odd also. Like then I can get for everything. Okay, if I can solve this problem, this is for even number of strings that can have perfect matchings. But now this is n1 times n2 times up to so on, like number of ways you can split these things into like this. We have to find this too. Do you guys get little bit? My throat also has some stamina, bro. It's hurting. So what I mean is, it's like number of ways you can split them into these subsets, and then dp of the smaller subset times dp of the smaller subset times dp of the smaller subset times this product we have to get. How to brute force this product is what I'm trying to see. Okay, how to brute force this product? How to brute force this product? Let's say this is 1, okay, and this is some odd size where all these components are even. I will brute force by choosing the subset of 2. If I fix 2, what is its subset? Choosing some even size elements, right? Choosing some even size elements. And once I select the subset of 2, Okay, subset of 2 is specific, right? Once I select the subset of 2, all of this is nothing but some odd number of things forming subsets, right? I have to fix subset of 2 so that it becomes unique. Once I fix subset of 2, and then I will count number of subsets of 2. So that has been separated. And then this thing can be seen as odd length because all of them are even with a lesser size. So that odd length lesser size times subset of 2 size into whatever this size is. Okay, that will be the DP answer of this. And for this, I have the DP answer. Do you guys see how I'm using recursion? It's a bit difficult, but let's see from the start. If there exists a perfect matching, what does that mean? Let's say these two are perfect matchings. Okay, size should be even, total size is even. Perfect matching means you pair them perfectly. If you are pairing these two, once you remove this will be odd size, this will be even size, and they should form perfect matchings among themselves. That should happen for all other even things. They must be even and they should form perfect matchings among themselves. And if you see this, the top is gone. So now childhood things should form. So whenever n is odd, the structure is leaving top. How many perfect matchings? How many trees can form perfect matchings? If I have this for n is odd and if I have this for n is even, then here I will brute force the odd subset. Odd subset is unique, but even subset here is not unique. That's why I'm fixing 2 to make it unique, to make it disjoint. Both are done. So now I'll code it simply. N square. I will use non-empty subsets everywhere. So dp of 1 is 1. Why? There's only one tree, right? For int n equals to, or n equals to 1, n less than kaplan n plus plus. Now, if n is odd, else if n is even, there exists an odd subset. Because if n is even, there exists an odd subset. Let's brute force that subset. Okay, you have n minus 1 things other than 1. Keep 1 aside. Number of ways to choose 2 power n minus some odd subset is 2 power n minus 2. Okay, let me just have p22 for no reason, powers of 2. Okay, so now if I can brute force this without making it unique because it's already unique. There is only one odd subset, and then I'm fixing that odd subset. Now I fix, see, DP counting brute forcing. You guys should get better at brute forcing. Okay, here I'm not brute forcing some subset because then I cannot differentiate that with some other subset. So I will fix 2, and then I will fix that subset so that that will become unique. And then this thing has a bijection to some smaller odd length subset by fixing 2. Here, once you remove the odd subset, you have this even thing. Okay, this is also odd thing, right? And that odd thing will have, once you remove this odd thing, this will also be an odd thing, and then that odd thing will have a bijection because this subset is just attaching to the top thing. There will be a bijection to that. So now dp of, I will fix this size 2. I will fix this size 2. Okay, let that size be z. If that size is z, number of ways to choose that subset is, there definitely exists one odd subset, right? 2 power z, 2 power z. Number of ways to, I am fixing size 2. So number of ways to choose that is, it's ncz. Okay, it's ncz. So I want ncr2. I don't want 2 powers, but I want ncr. Even here, I will fix the subset size. So I don't want 2 power, I want ncr. So how will I make ncr? I will just make an NCR array easily. Using NCR recursion formula, my implementations are clean, right? Clean means I won't Google, I won't load some big template to find NCR when I have beautiful NCR recursion formula. Why would I do that? To type it quicker. NCR plus NCR minus 1 equals to n plus 1 CR. NCR plus NCR minus 1 equals to n plus 1 CR. Okay. If j less than n, would this work? J less than n, j is less than n, j minus 1 less than n, everything's less than n, it works out well. I greater than 1, everything works out. It works out. I need not consider 1 also. The formula works even after bounds, it works. Even after bounds, it works. Maybe it works on negative numbers too, we don't know. Reminder m. So now where am I? All I need is NCR, and I will make sure that that size will be in the bounds. Okay, size of that odd length subset. I will make sure that it is less than or equals to n minus 1. Okay. So now we are having that odd length subset that can be chosen. How many ways you can choose that from n minus 1 subsets? We are choosing a subset, and for a subset of indices, we have this defined, because after you choose a subset, even if their indices are in increasing or not consecutive, if they are increasing, it's similar to 1 to n, right? It's similar because you cannot attach a small bigger thing to only a smaller thing. It's just renaming. So dp of n plus equals to, so how many, I'll just make it pos equals to NCR of n minus 1 of z. Number of ways you can choose a z length subset from NCR things, and then pos times equals to, what is it? Or you choose it, and then you make it perfect length permutations. This one, okay. And then what is the remaining thing? N minus z is the remaining size, right? But here, how I brute force is, because everything else is even here. Every small subset is even. But I fix subset that involves 2. Okay. If I fix that subset that involves 2, now again, its size is odd. Why? Because now we have all even length, but if this is 2, all of them are odd length, right? All of them are odd length. Z equals to 1, z less than or equals to n minus 2, because 1 and 2 are already outside. In these many number of ways we can choose that 2 subset, 2's even subset. In these many ways we can choose that. If it is in bounds, this works. Z greater than 1. If it is in bounds, this works well. Okay. I mean, sometimes we have to return 0, right? If it is out of bounds, but then it's in bounds. So number of ways this will work. It's z plus 1 here, okay, because 2 is also considered, right, along with them. And what about other things? N minus of z plus 1, or the remaining things. So now I'm seeing all the remaining things as a one thing, because they're one thing, right? And then it's just 2 subset is just getting attached to that. They are one thing. They're one odd thing. Sorry, they are one even thing. They are one. No, wait a minute. They're one odd thing. They're one odd thing because this is even. Even has gone, so they're again still one odd thing. If sample passes, we will pass this. So done, guys. It's a simple brute force. We don't even need theorems, much of theorems. Okay. Again, if you have clarity, implementations are not that difficult though. It's giving clearly, right? Now everything is working. Except the fact that we are returning 0 after 0. Okay. Because I have to start from n equals to 2. N equals to 1 was initialized. My definition is different, right? My definition of DP is different, right? Whenever n is odd, I am forming not a perfect sequence, but then I'm forming leaving one aside, trying to form perfect sequence because that's being used here. Top thing is gone, you have to form that. We want probability, not just this one, right? So let's see the samples. Now I remember the problem. If you see the samples, they say no explanation. What is this value? We can't check that. We can't check that. So we want probability, right? What are the total number of possibilities? I just counted what are the number of possibilities. What are total number of possibilities? It's just P2 has P1 has, I mean, I equals to 2 has Pi minus 1 choices. Means it's like for I equals to 1, 1 factorial because 2 must go to 1. 1 into 2 into up to so on, n minus 1 factorial is the answer. We have to just divide with that. So now we need mod inverse because we have to divide with that, right? We need mod inverse. Mod inverse is not that complex, guys. You can just write power of this rest equals to 1. If you write it 10 times, I might have written it thousands times. It won't become that difficult to write it again. Okay. But you will write mistakes like this. So we have to do y by 2. This is binary exponentation. You can think how to find 2 power 100. Split it into 2 power 50, 2 power 50. If you know 2 power 50, you can know 2 power 100 just by doing square. Okay, now 2 power 50, how do you get? Maybe 2 power 25, if you know, you can get 2 power 50 easily. Now 2 power 25, how can you get? Keep 2 aside, 2 power 24. Maybe 2 power 24, you can split it into 2 power 12 times 2 power 12. That's a small problem can be given to some just small kid with a calculator. They can do binary explanation. Don't complicate that. Now with all the factorials I'm finding NCR like this is unnecessary. Now I want factorials, right? Now I want factorials. Okay, it's just n factorial. Now I want n factorial, right? N inverse factorial, let's say. Okay, inverse n factorial. Because I have to multiply dp with inverse n factorial. Done. That's done. So now I'll simplify this further. And answer equals to dp of n times in fact of n minus 1 because it's n minus 1 factorial. Then I'll write answer here. Past. Do you guys see the clarity I have and how I solve? Simple. Not that difficult. Submit it and sleep. How is n squared not allowed on this? How is n squared not allowed? It's too much. N squared should be allowed on this. Okay. Is it failing on test 1? 3 seconds. Okay. It's failing on test 1 itself. If n square is not allowed, we can't do this problem right now because then we have to think of some better ways. Okay, if n square is not allowed, we cannot do this problem right now. We have to think of better ways. If n square is not allowed, if n square is not allowed, we can't do this right now. But for n equals to 10 power 4, n square should be allowed, right? All I really know is that they don't really care about us. I'm ending, guys. This doesn't help much. Maybe I'm foolish, maybe I'm blind, thinking I can see through this and see what's behind. But no way to prove it, or maybe I'm blind. I'm only human after all. I'm only human after all. Don't put your blame on me. Time limit is 3 seconds, but then the limit is 2 seconds. What the fuck was that? Is it due to accessing arrays? Is it like array accessing causing this thing? NCR is better as a array, right? Direct access instead of calculating. It's a secret group, bro. You cannot get in. You have to find it. It's Illuminati. I'm just joking. It is on post, bro. It is on post. Okay, n square is working with point 0.1, 0.01 seconds. But then it becomes 100 times when we increase this by 1 0. Chef is shitty. What do they want? Why isn't 10 power 4? It could have been 5000 also should be working, right? With this thing. Was this wrong? Is this taking too long? So often, right?
Maybe I'm foolish, maybe I'm blind. Thinking I can see through this and see what's behind. Got no way to prove it, so maybe I'm blind. 'Cause I'm only human after all. I'm only human after all. Don't put your blame on me.
Maybe I'll write DPFN here. That doesn't change a thing, but I can't make this summation in a better way. I can't store this in a better way because as Z increases, the products keep changing. It's like conversion, right? Now it's 0.01 second, but then if I just add a 0 here, it's 3 seconds. But 3 seconds and 2 seconds are not that far, right? It's stupid. 3.1 seconds. So should I just try to eliminate, optimize these small things? I don't think this very well. How to do some optimization inside n square, right? Inside n square. Any optimization inside this will help. So. So this size is what? Odd. This size is what? Odd. Am I recalculating something twice? Am I recalculating something twice? If you look at this and if you look at this, but then dp of z plus 1 this is dp of, but this is dp of z. Odd. dp of z plus 1. I'm not recalculating it. Would this be better? What for? Yeah, I'll sleep in some time. But what is Code Chef even about? Like, what do they want to test? Now it's 3.19. I'm leaving, guys. I gave you solution. I gave DP. I think that's enough. Bye. I'm ending the stream. Bye, guys.